section 8, and that'll be our day. Sound okay? Sounds amazing, doesn't it?
No.
No. Wow, that's honest. All right. Questions from homework that anybody has? Okay. I'm holding. 20 minutes?
And I have like 5 different notebooks that I have to work with. Okay. So for the ones, like, well, actually, this might have been the other day. No. What was last night's homework?
We should be through 56, I think.
Okay, well, I mean, I didn't get all the way there.
No, I don't know. Wouldn't have
So the
expected
ones that
it.
are like for like 33, for example, like the Y, like coordinates are only like 1.
Okay.
So for the range, would it just be 1?
Yeah, it would look like that.
Okay. Yeah, that's it. All right.
That's easy. Cool.
Yeah.
Jackson.
On number 42, I just couldn't read the graph.
Oh, yeah, I put that too. I wrote literally.
Oh,
read
yeah,
the
just
graph.
you can skip it. It's fine. Whatever. Yeah, there's this. I didn't. Yeah, the embedding didn't go very well. So if you couldn't read it, you can just say, can't read it, can't do it, just skipped. That's totally understandable. Or you could make up some numbers for them if you wanted to, like whatever. It's one problem. At that point, you kind of get the idea by that point. I think you've done, 10 of them that are fairly similar to that one. At that point, you get it. So that's fair, though. Okay. Who else? Do we have any others? Jackson, go ahead.
On number 47, when I was finding the domain, I got everything else right. So for finding the domain, I got a different domain.
For 47?
Yeah.
Well, let's look at what the answer says. Oh, that is a bizarre looking domain, huh? That certainly seems to be incorrect to me as well. So we'll, I think that's, you probably said what, -5 to positive infinity? Yeah, that's, I think that should be the correct answer. I think there's just a mistake there. You said 47. Okay. Yeah, I agree with that. I think that's probably just a mistake. Raylan, did you have your hand?
Oh, yeah. Could we do 48?
Sure. We'll go back to this. So we're asked to do a bunch of things for 48. We need to do all the things?
Oh, so can we
Okay.
just do like the solving part?
Find the inverse?
Yeah.
Okay. Yeah, no problem. So we have y equals 3 over x plus 4 minus 9. So what I would do here is I would, well, let's ask you, what did you want to do first? What was your first instinct?
To add the 9.
Okay, totally fine. And then what was our idea?
And then would you have to do
Okay, you multiply both sides by x plus 4?
Yeah.
Yeah, I like that idea, sure. So that's going to be y plus 9 times x plus 4. It's equal to 3. Okay. What you'd want to do here is you'd want to FOIL the left-hand side out. So you'd have xy plus 9x plus, what is that, 4y plus 36 is equal to 3. Is that okay? And from here, let's get all the stuff without x's out of here. So we'll just subtract the 4y over and then subtract the 36 over. We can factor off an x and then divide both sides by y plus 9. And there we go. So the last thing would be to just swap the x's and y's. And that'll do her. Is that okay? So it looked like you were in a good spot. You just need to kind of keep going.
Okay.
But all the what you described to me doing was good. That was correct. So yeah. You're on the right track. Anybody else? Yeah.
Can you do 56?
Alyssa, yeah, sure. So here we're asked to just verify that the two things are inverses. Of course, of course. So to do that, we need to do f of g of x, and then we need to do g of f of x, right? So f of g of x, so our f is 3 times e to the x plus 1, but instead of x, we're going to write in the function for g. So there's the composition. Is that okay? So right away I can see that the plus 1 and minus 1 are going to cancel each other out. And then the exponent base e and the log base e will cancel each other out. Oops, forgot to write the minus 5 there. So I'm left with 3 times x plus 5 over 3 minus 5. And the times 3 and divides by 3 cancel out. And the x plus 5 and the x minus, or the plus 5 and minus 5 cancel out, and I'm left with just x. Alyssa, is that okay?
Yeah, thank you.
Sure. We got to do the other direction. Do you need to see that one too? Sure, no problem. Just checking before we, you sounded like you're like, oh, okay, I'm happy with that. And I was like, oh, we have another side to do. So g of x is the natural log of x plus 5 over 3 minus 1, but instead of x, I'm going to write g, which is 3e to the x plus 1 minus 5, and then I still have the plus 5, and then divide by 3, and then the minus 1. So minus 5 and plus 5, get out of here. So that's the natural log of x plus 1, or 3 times the natural log of x plus, the natural log of 3 times e to the x plus 1 over 3. times 3 and divides by 3. Yeah, out of here. Oops, forgot my minus 1 there. It gives me the natural log of e to the x plus 1 minus 1. Log base e and exponent base e cancel. See you later. And I'm left with x plus 1, and then minus 1. The plus 1 and minus 1 cancel. And I'll have to do it again with just x. Is that cool, Al?
Yep, thank you.
No problem, my dude. The last call on questions before we move on to something else. Okie dokie. Section 8 then coming up. Find my notes here. Okay. Section 8 is about graphical transformations. So the idea here is that I can take a function and think of any function of the same family as a transformation of that original function. So let's say we have some function f of x. That's the original. We call that the parent function. And the transformation that we can do to it is, let me just double check and make sure I have that written the way I want to. Okay. A times f of 1 over c times x minus h plus k this we'll call the resultant function. So that resultant function is going to look a little bit like the parent function, but it'll be changed based on the transformations that are applied to it. So think back to your geometry class. I know that was a long time ago. You talked about transformations there. Does anybody remember one of the types of transformations you would have talked about in your geometry class? I know it was a long time ago. John?
Like shift left and right.
Yeah, so those are called translations. So that's shifting the graph or shifting left and right. So we have two types of translations. We have vertical translations. And what controls that vertical translation is the plus k at the end. If k is negative, we're going to go down that many units. And if k is positive, we're going to go up that many units. Is everybody okay with that? The other type of transformation that we'll deal with is horizontal. For the horizontal translation, we're going to apply that change directly to the x coordinate. So if that value for h is negative, we're going to be going left that many units. And if it's positive, we're going to be going right that many units. So just to give you a visual of kind of what we're talking about, let's say that our function is just, our parent function is just x squared. If I do x squared plus 2, that's a positive value for k, so I'd expect the graph to be moved up 2 units. So here's my graph for f, there's my graph for f plus k, it's moved up 2 units. Everybody okay with that idea? If I do x minus 5 squared, there my h value is a positive 5, so I'd expect the graph to be shifted 5 units to the right. If I look at the graph, there it's been moved to the right. It looks like 5 units. Is everybody okay with kind of what we're saying here? Okay, good. What's another type of transformation that we can remember? Jackson?
Like stretching and shrinking.
Good, yeah. So stretches and shrinks, we called those guys dilations, I think is what we called them in our geometry class. We'll call them stretches and shrinks still, though. Here. So we had 2 types again. We have vertical So the vertical stretch or shrink is going to be controlled by a multiplicative factor being applied directly to the f of x, or to the entire function. So this is a, when the absolute value of a is greater than 1, it's a vertical stretch by a factor of a. And if the absolute value of a is less than 1, it's a vertical shrink by a factor of a. It's okay with that? Again, we'll look at some pictures here in a second. We can also have horizontal stretches and shrinks. So again, the horizontal is going to be applied directly to the x coordinate. So we have 1 over c times x. And we can say the same thing, that when that c is bigger than 1, it's a horizontal, stretch by a factor of c. And if absolute value c is less than 1, it's a horizontal shrink by a factor of c. So let's see here, do an example. So we're still going to use x squared as our function. So if I do like 2 times x squared, the graph should be stretched vertically, so it should get like taller and skinnier. Which is what we saw, right? If you pull it up, it's going to make it taller and skinnier. If I do 1/2 times x squared, like that, it's going to make it shorter and wider. If I graph, here's it getting wider. Everybody's okay? Now, if I apply these directly to the x, so like if I have 1/2, that c value is greater than 1, I'd expect it to be horizontally stretched, would also make it like shorter and wider, right? So there's the parent. There's shorter and wider. Everybody's okay with that? And say, like, if I pick a c that's less than 1, so maybe 0.5. Now, typically, we wouldn't write it as 1/0.5. We'd write it as just 2. Everybody's okay with that? But just for clarity, I'm going to do that. So here I'd expect it to shrink horizontally, which is going to make it like taller and skinnier, right? Which is what you're seeing. Does that feel okay? All right. So that's 2 translations. Do you guys remember any others? Jackson?
Flipping over like the axis.
Yeah, so that's a reflection. In geometry, you probably talked about several types of reflections. Here, we're only going to talk about 2. So there's going to be reflection across the x-axis. So that's controlled by that same A coefficient that controlled the vertical stretches and shrinks. So if A is positive, we have no reflection. If A is negative, we get that reflection across the x-axis. And then we can also reflect against the y-axis. The C coefficient also is going to take care of that one. Again, if C is positive, there's no reflection. And if C is negative, again, we reflect across the y-axis. Everybody okay with that? There's a 4th type of reflection or type of transformation talked about in geometry called rotation. That's not something that we're going to deal with in a course like this, and really in your high school career. You wouldn't talk about like rotational transformations to functions. It's beyond the scope of what we're doing. In fact, you'd need the trigonometry that we do in this course to even start talking about like how to do that type of a transformation. So we're ignoring that. Okay? So if we talk about, okay, what if I have multiple of these transformations occurring to the same function? Like what order would I want to do these transformations? So the first one we do is the reflection across the y-axis. Then we do the horizontal stretch or shrink. Then we do the reflection on the x-axis. And then the vertical stretch shrink. And then we go do the horizontal translation. So shifting left or right. And then the last thing is the vertical translation, the shifting up and down. So if I look at a function, I identify all these different transformations, and I go to graph it, and I'm trying to do it step by step. I take, the first thing I do is the reflection across the y-axis, get a new graph. Then I take that graph and I stretch it horizontally or shrink it horizontally, get a new graph. I take that one and then I do the next one. You may go.
For the ones affected by A and C, does it matter which order you do those in as long as they're before the H and J one?
So, does it matter?
Like, could you do all
Okay, yeah, so I know what you're saying, and the answer is really kind of no, but it's much more convenient to do the horizontal stuff first because that stuff is inside the function as opposed to the vertical stuff that happens outside the function. So no in reality, but in practical terms, it's a little bit more convenient to do it in this order. Yes, that's what I thought you were going to be asking me because I saw the empty bottle. Of course. Okay, so let's do some examples then, yes? Does that sound good to you guys? All right, so we've delivered like really all of the content, all the theoretical content here. We identified these types of transformations, we showed how to represent them, and now really what I'm going to do is just do some examples on like questions that you might run into in something like your homework. Okay. So let's say that f of x is the function 3x squared minus 4x plus 1. And let's say that I want to reflect across the x-axis. So if I'm reflecting across the x-axis, this implies that the a coefficient is negative. And if all I'm doing is reflecting across the x-axis, this is really implying that a is negative 1, right? Because I can't have any stretch or shrink, which would give me a value for a that has to be bigger than 1. The absolute value of a would have to be bigger than 1 or less than 1. So if the only thing happening is a reflection, then that a has to be specifically negative 1. So my new resultant function is just going to be negative f of x, which would just be negative x squared plus 4x minus 1. If I was reflecting across the y-axis, that would imply that the c is negative. And since there's no additional translation, I know that the c is negative 1. So my resultant function would be f of 1 over negative 1 times x, or really just f of negative 1. Or, I'm sorry, f of negative x. So if I do that, 3 times negative x squared minus 4 times negative x plus 1. So that's 3x squared plus 4x plus 1. Okay with that? What if I wanted to have, say, like a vertical stretch by a factor of 3 or something? Since we're talking about a vertical stretch, that tells me that it's an A, because it's not talking about a reflection. I know that A has to be positive. And because it's by a factor of 3, I know the A has to be 3. So in this case, it's just going to be 3 times f of x. So 3 times 3x squared minus 4x plus 1, or 9x squared minus 12x plus 3. What if I want a horizontal shrink by 1/2? Well, since we're talking about horizontal stretches and shrinks, I know we're talking about the C. Because there's no reflection mentioned, I know that the C needs to be positive. And because we're shrinking by 1/2, I know that the C needs to be 1/2. Yes, sir.
May I use the restroom?
Certainly. So 1 over 1/2 is really just 2. And if I do f of 2x, I have 3 times 2x squared minus 4 times 2x plus 1. 2x squared is 4x squared, and then 4 times 3 is 12. Just mentioning where the 12 is coming from. Right? 3 times 2x is 12x squared. We're good? Okay. E. What if we do a vertical shift? Shift of 4 units. Since we're talking about a vertical translation, that tells me k, and since it's, oops, I need to have shift up. Since we're going up, I know it's positive, and since it's 4 units we're moving, it has to be positive 4. So g of x is going to just be f of x plus 4. So 3x squared minus 4x plus 1, and then the plus 4 at the end. Everybody okay there? So again, we're just transforming our original function based on the description of what we want to do. What if we're doing a horizontal shift left 3 units? So this time, since it's a horizontal shift, we're talking about the h. Since we're going left, I know the h needs to be negative, and since it's going 3 units to left, h should be negative 3. So there's that. So really we're doing f of x plus 3. So when I do that, then it's like a composition. So I'm replacing all the x's with x plus 3's. Now I'm going to have to FOIL out the x plus 3 and then distribute the 3. I'm going to do that all in my head. Is everybody okay with that? In the interest of saving some time here. Oops. So when I combine this all back together, see, plus 14x minus 28 minus 12 is 16. Okay there? What if we combine this into like a multiple steps? What if we say we want to be specific about the order, A, B, C, D, F, G? So what if we want to do a vertical shift by 3, and then a vertical stretch by 2. Probably say up here. So this tells me that k should equal 3. So my first function is going to be f of x plus 3. And then after it, my next function is going to be, well, a vertical stretch by 2 tells me that a has to be 2. It'd be 2 times that g of x. Right? So I'm going to take what I had after I did the stretch or the shift and then apply the stretch to it. So in this case, 3x squared minus 4x plus 1 plus 3 gives me 3x squared minus 4x plus 4. And this gives me 2 times 3x squared minus 4x plus 4, which is 6x squared minus 8x plus 8. That's going to be my final. Is everybody okay there? Notice here I was told a specific order to do the transformations. Do you think it matters the order? You better believe it. So if we just wanted to do, say, the reverse, I'm just going to write it that way, the reverse order of G. So instead, we'd have 2 times f of x, and then I'd have g of x plus 3. Is that okay with everybody? You'll notice that we'll get a slightly different answer. Oops. So we have 2 times f of x. Give myself some space here this time. I was smarter. And you notice that those are not the same, right? Worth noting. Okay, yes, of course. Okay. Let's do a different kind of example. Let's ask you to describe the transformation to f of x. I should write y equals f of x for the function g of x equals 2 times f of x plus 1 minus 4. Oops-a-daisy. All right, so to do something like this, what I want to do is I want to start by identifying my values for A, C, H, and K. Oops. So in this case, my value for A is 2, right? My value for C is 1, right? Because what's the coefficient on x? Just 1, so 1 over 1. My value for H is -1. Again, we got to be careful with those H's because they're the opposite of whatever it looks like because of that negative sign. And then the K is -4. Once we have that, we can write this in order. Since the C is greater than 0, we have no reflection across the y-axis. Since the C is equal to 1, we have no horizontal stretch or shrink. Since the A is positive, we have no reflection in the x-axis. But since the absolute value of A is greater than 1, we have a vertical stretch by a factor of 2. Since h is -1, we know we have a horizontal, or we're gonna, well, let's just write shift left, since it's -1 unit. And since the k is -4, we're gonna shift down 4 units. What do you guys think? Again, not too bad, right? The hardest part is pulling out the values for A, C, H, and K, and once you do that, it's just following the rules that we stated before. Let's do a different kind of example here. So let's say we're given the function f of x equals 2x squared minus 3. And we ask you to describe the transformation in the proper order, of course, to get g of x equals -6 x plus 1 squared minus 1. Okay, anybody with an idea here as to what we're going to do? So you could start by trying to find the values for A, C, H, and K. That might be a little bit harder than taking a different approach. So my approach that I would take is I'm going to go and I'm going to walk through the 6 possible transformations and just kind of compare the two and figure out what I need to do for each of these 6 transformations, and then do the change there, look at what I got, and just kind of step by step through it, which I think will be easier than hunting these A, C, H, and K directly from jump. Does that feel okay? So the first thing we'll look at is so basically what I'm going to do is I'm going to say, okay, well, my initial function is just going to be my f of x. Let's write it this way. And if I look at this, there does not appear to be a negative sign inside my function when I look here, right? The sign on the x is still positive, right? I mean, there's a -6 times the outside, but inside the parenthesis, the x is still positive, right? So I think that there's no like reflection on the y. So any c that there might be is positive. Everybody okay with that? Okay, so we didn't really do anything there. And, oops. Oh my goodness. All right, let's set it this way. G1 is equal to f of x. G2 is going to equal G1. So the second thing I look for is a horizontal stretch and shrink. To do that, I'm going to look at the coefficient on the x. So if I look inside the parenthesis, the x is just 1x. If I look at the original, if I think about it like inside a parenthesis, it's still 1x, right? So again, we see no horizontal stretch or shrink. And from these two, basically we're saying that C is 1. So the next thing we're going to look for is a reflection across the x-axis. I do see that there, right? So G3 is just going to be the negative of G2. That'll get me my reflection that I'm looking for. And so my function has changed to negative 2x squared plus 3. The next thing I'm going to look for is a vertical stretch or shrink. I notice that my leading coefficient is now bigger than it was before. How much bigger? 3 times bigger, right? Okay, then we're going to look for shifts left and right. So I notice that I have this +1 inside. So I am going to be shifting left 1 unit. Maybe we should keep doing that. Is everybody okay with what we've done so far? And then the last piece here to get my end, if I compare the number at the end that I had before, it's currently 9, needs to get down to -1. So I have to subtract 10. So I'm going to shift down 10 units. That is, k is -10. And I think going at it one step at a time like that, one transformation at a time, I think makes life a little bit less daunting than trying to grab it, go straight, attack straight at it looking for them. Like the C is easy to come up with. You can probably do that on inspection. And maybe even the A, not so bad. But coming up with the decay was -10, I think would have been pretty tough to make that conclusion without kind of stepping through this. Okay, I have one more example problem to do and then we're finished. So what if we have the function f of x as described by this graph? And let's say we want to, so this is my f of x, and say we want to graph g of x equal to 2 times f of x plus 3 minus 1. So here's the trick, is that, I'll write it in a different color. xy in my f of x is going to go to cx plus h times ay plus k to get my point in my g of x. So that's my map for transforming a point in F from my parent to a point in G, my resultant. So to answer this question, I need to start by identifying my values for A, C, H, and K. What's my value for A? 2 is correct, right? What's my value for C? 1, that is correct. Again, the leading coefficient on X is just 1. My value for H is -3, very good. Remember, the H is the opposite of what it appears. And then the K is -1. Okay, so in our case, our map is going to be x minus 3 and then 2y minus 1. So my first point that I'll plot is -5, -1. So -2, 0 turns into -5, -1. Is everybody okay with that? And then 0, -2, well, that's going to turn into 0 minus 3, 2 times -2 minus 1, or -3, -5. 2, 0, well, that's going to be 2 minus 3, and then 2 times 0 minus 1, or -1, -1. And then my last point was 4, so that'll be 4 minus 3, and then 2 times 4 minus 1. So that'll be 1, 7. So far, so good. So now I'm just going to go back to the original graph and plot these points. So -5, -1, so I don't know, over here somewhere. -3, -5, I don't know, down here somewhere. -1, -1 is over here somewhere. And then 1, 7 is maybe like up here somewhere. So there we go. So if I take a look at this, it looks like we've been shifted left and down and stretched vertically, which should jive with what we observed from our A, C, H, and K, right? And that's that. Yay! So that allows us to finish things up. That'll be 57 to 66 will be the last of things. That's going to close out chapter 1 for us. So just to talk about the homework schedule and the schedule for the rest of the stuffs. So this homework check for this weekend is going to be for 23 through 56. And I know the homework check in the book or in the grade book says Sunday at midnight. Realistically, I'm not going to look at it till Tuesday morning. So like, you know, if you're done, if you want to work on things Monday, that's totally fine. Not a big deal. I'm not going to change the due date just because I'm too lazy to do that, but I'll tell you that it's totally fine to work on it still on Monday. Then 57 through 66 plus the chapter review is going to be due the following Sunday. And then we'll be looking at our chapter 1 test probably the end of next week. So the next class will have a day to just ask questions and work on the review. And then the following class we'll do the test. Is that okay with everybody? And should get the